All right, folks, we are going to get started on sections 5, 6, and 5, 7. We do those together, or at least I'm going to do them together just because they both cover the law of sines. Now, as we move into 5, 6, 5, 7, 5, 8, we're dealing with triangles again and solving triangles. Remember, we were solving right triangles in the earlier part of this chapter. And in that part, we were given two pieces of a right triangle, you can find a third piece, or you can solve for the entire triangle, all the other pieces. If you're given two pieces to start, knowing the relationships and those ratios in a right triangle. Well, now, if we're given a triangle that we do not know whether it's right or not, is there a way or is there a strategy that we can still solve for the missing pieces of the triangle? And there is. If we don't know a triangle, whether it's right or not, or in the case that if it isn't a right triangle, we have to have some strategies, and there is one. There's a few that we can use. Now, the difference is with a right triangle, we only needed two pieces of information, as I just mentioned. But with a triangle that is other than right, we would have to have three pieces of information. And according to what three pieces of information you're given, just like you would see in your right triangle, if you were given the opposite side and an angle, and you wanted to find the adjacent side, you would be using tangent, right? Because you found what went with it. Same idea here. Given certain three pieces, we'll go to a different strategy, all right? Today, we're going to start in 5, 6, and 5, 7 with law of sines. Now, law of sines, I'm going to go over to our notebook and get started here. With law of sines, what we're talking about is the law itself. I think you guys are probably familiar with. If not, it's the idea that the ratio of the side length of any triangle and the sine of its angle, the angle and the side opposite, I guess you could say is a better way, that ratio is going to be consistent throughout a triangle. So if we have a single pair, when I say a pair, I'm talking about a angle and its side opposite. Whoops, I'm talking and writing wrong. All right, already. All right, anyways, sine C. If we have this for a triangle, and let's just draw a basic triangle, that if we had any triangle where we could label side A or angle A, B, C, and that would make this side A, this side B, this side C. So when we're talking about A over sine A, we're talking about this side length over the angle opposite, right? That the side is opposite the angle itself. So that's what we're talking about. These ratios will stay consistent in a triangle. So if we know one of these pairs and say I know side A and sine A, I can, if I'm given side B, I can find sine of B, and that will lead me backwards to find angle B. And then we can use that to find the last angle and so on. It gives us pieces to build the entire triangle so we can find all of it. So let's see how that works. So first thing, I said we needed three pieces of information. One set of information, whenever you're given a problem, what I want you to do is analyze, what did they give me? The first situation we're going to talk about is when we're given two angles and a side. All right, when we're given two angles and a side, you got to think about what that means. If I have two angles of a triangle, and we know that the sum of the interior angles of a triangle equal 180, we can quickly find the third angle, can't we? And so if we have two angles and a side, and let's look at that same triangle up there. So if we said we had like angle A, angle B, and side B, well, we could quickly find angle C and then use this to find the other pieces because we have a pair. Notice if you have this, like you could have A, B, we could have angle A, angle B, and side A. These are all angles that are, we've got two angles and any side that we could talk about. So we could have, let's see, well, you could just keep going. We could do angle A, angle B, and side C, and all the other combinations. You could do angle A and C in a side, angle B and C in a side. So it's always going to work out that given this, we can go back and recreate pieces. We have a pair, I'm sorry, A, B, and C. Yeah, we could do that for any of those, I'm sorry. So let's look at an example for this. I think it's going to be easier to see once we get into it. Anyways, All right, for example, if I gave you, let's say, solve this triangle. All right. So when they say solve the triangle and they give us that angle A is 38 degrees and angle B is 63 degrees and side C is 15. All right, so we are given the pieces we need. We're given 3 pieces. So with this, I don't have a pair yet, but I can find angle C right away, right? If I find angle C, and angle C, we know that angle A plus B plus C equals 180. So if I take 180 degrees minus the other 2 angles we were given, 38 degrees and 63 degrees, I end up with, what is that, 90, 101 degrees, so 79 degrees left. So angle C is 79 degrees. Wow, that looks horrible. Let's just clean that up a little bit. So angle C is 79 degrees. We've got one of our pieces already, one answer blank answer, right? So we got that. Now we also have a pair because I have no side C. So now I can use that ratio, 15 over the sine of 79 degrees is equal to, and we can go for, I usually go to the next largest angle, whatever is the largest one, the other one left. So I'm going to do length B over sine of 63 degrees. And then I just need to solve this. And solving this, this is a proportion, so I can just cross multiply. So I would have 15 sine 63 degrees equals B sine 79 degrees, which makes B equal to 15 sine 63 degrees over sine of 79 degrees. So that's equal to B. So now, again, going to my calculator, make sure your calculator's in the right mode. You always have to double check that you are in degree mode when we're using degrees and so on. So I have 15 sine 63 degrees, and that's going to be divided by sine of 79 degrees. And we're going to get 13.615. And so B is equal to 13.615. And most of these problems will tell you to go to the nearest tenth. So we'll call it B equals 13.6. So we have one of them, one of the sides we were missing. Now we need to get side A. Well, again, I can go back to what I had here and do the same thing again. I can go back and say 15 over sine of 79 degrees is equal to length A over sine of, I believe it was 38 degrees. Yes, 38 degrees. So sine of 38 degrees. Now we know then A is going to be equal to 15 sine 38 degrees over sine of 79 degrees. And when we punch that in our calculator, we end up getting 9.4077. So we'll call it 9.4. And we have our triangle solved. So that's pretty straightforward. When you're given two angles and a side, you can use this process. All right. So now the big time consumer, this is going to take us a little bit, so get comfortable. We got to go through what happens when we are given another situation. This is a different one. Instead of two angles and a side, if we are given two sides and the non-included angle. So now we need to talk about what it means to be or have a non-included angle. So let's look at our triangle again. If I build a triangle, ABC, and let's label it. So we'd have A, B, and C. All right. So if I take two sides, say I take side A and side C. If I take side A and C, that's these two. this would be, angle B would be the included angle. All right, it's the included angle because its vertex is created by the two sides we talked about. That's the included angle. We want a non-included angle, so A or C. So if I had angle, length A, length C, and angle A, I would have two sides and non-included angle. Or if I had A, C, and angle C, I would have two sides and non-included angle. If I had A and B, well, A and B, C is the included angle, so A would be the angle. That would work for this situation. A, B, and angle B would also work. If I had B and C, well, B and C make angle A, so I can't use that, so I'd use angle B. B and C also, I could use angle C. Now, if you notice something about this and you think of law of sines, if I have AC and A, I have what I call a pair. I've got the angle and its side opposite in each one of these, don't I? Every one of these, and these are the only ways we could get two sides and non-included angle, every one of these has the pair of the angle and its side opposite. So we have one of the ratios in the law of sines automatically. There's a problem though with this. And the problem is kind of complicated by one thing and one thing only, is that first off, you have to figure out, if I drew this, what would it look like if I had two sides and a non-included angle? All right, so if I have two sides and a non-included angle, what I have is, let me draw another triangle. All right, so this is an example. If I know I've got a side here and say a side here, whoops, I gotta bring that down. And we know this angle between them. All right, so we know this angle. Let's say this is angle A. All right, we also know this is side B. This is part of angle A, because the non-included angle does have one of the sides, right? It just doesn't have the other one. This is not side A. So it wouldn't work. But this is true. So we know where in space this point is, because it's this angle away from this line, and it's this distance from that point, right? From this vertex, A. So we know where that is in space. We don't know where this line ends. This line goes on forever, kind of into space. So when we go out here, this thing just goes on forever, right? We don't know where it goes or how far out it goes. We just know it goes out that way. Well, I don't want that dotted anymore. Let's go back to this. Let's see. It does not want to give me that. I'll do that. There we go. All right, so that goes on. We don't know how long. Now, so far we've dealt with the fact we have A and B, right? We have angle A, side B. With angle A, I could have over here C or any of the others, right? But I need a pair. So this one would have to be, let's see, I do have everything I need. This one out here, the thing about this one that's bothering us is we don't know this angle between this side and side B. So this could be anywhere out here, right? And so I'm just going to draw it kind of arbitrary length. And this is my side opposite. So if I have the angle A, remember I always have one pair, that means this side has to be the side opposite. So I've got this side opposite. It's kind of free in space. I don't know where it's at. So there's an issue here because this length is incredibly important. If this length is what I call the perfect length, if it's the shortest distance between this point and this line, it would come straight down this way, well, as straight as I can draw it, and it would make a right angle with it, wouldn't it? Remember, of your geometry, from any point in space in a line, the shortest distance to it is a perpendicular to the line. So, and through the point. So what if A is this perfect length? Well, if A is this perfect length, that just barely, it reaches exactly from here to here at a 90-degree angle, then our triangle ABC is a right triangle, isn't it? Because this would be our triangle. This down this way, and up. This would be our triangle if it has the perfect length. So it'd be a right triangle. And we would just use the right triangle trick. So when would this be true? Well, this would be true if when we have this angle and this side A, the side opposite, and the hypotenuse, because this is the hypotenuse now of a right triangle, we would know that sine of A would have to equal A over B. Or in other words, B sine A would have to equal A. So we could look, if we can take this side and multiply it by the sine of the angle, and it's equal to that side that's out there in space, we got a right triangle. So if this is true, then we have a right triangle, and you just use right triangle trig to solve this. All right, now it's not going to happen it's got to be exact. It's got to be equal to. If it happens, you've got a problem from earlier in the chapter, and it's much easier. Now, if it's not true, well, let's start looking at that. There's some other cases here. What if instead I have, let me get the right color. There we go. Instead of that, I've got a side out here that keeps taking that away from me. All right. I have a side that is out here, and it's just not long enough. It's like I drew, basically. It's like this type of length. It's this length. I'm going to put it down closer to the red line, which is the perfect length, right? I'm going to label that that way too, just so you know. I call it this a lot. So I'm going to call this PL, and this is the perfect length, right? B sine A. B sine A is the perfect length. It's the perfect length because it makes a right triangle, right? If A is equal to B sine A, or the side adjacent times the sine of the angle, is equal to the side opposite the angle, the one that makes the pair, then you have the perfect length and you got a right triangle. Now, what if it's too short? What if it's this length? All right, instead of being long enough, now no matter where I kind of rotate this, right? No matter where I rotate this piece, it's not going to reach this side. So if this length, A, is shorter than our perfect length, then we don't have a triangle at all. And that may be your best case, because then you don't have to, you can just put no solution. So how do we say that? How do we know that? It's when this side opposite is less than B sine A. So it's when our side opposite, A, oh, that's just lagged on me badly, guys. Sorry, that's why that looks so ugly. Side A is less than my perfect length, B sine A. Again, I'm getting some skipping. Sorry. All right, so B sine A. If this length is less, then when we have this situation, we have, again, it's less than the perfect length, that side opposite is, we have no triangle possible. So when there's no triangle possible, we just write no solution. Sometimes they're just going to ask you how many triangles are possible here. Sometimes they're going to ask you to solve it. If they say to solve it, you write no solution. If they ask you how many triangles, there's no triangle. All right. So we said if it's the perfect length, less than the perfect length, now what else do we have left to cover? Greater than the perfect length. So let's look if it's greater than the perfect length. So if it is, we would have this situation where we have a side that comes down here. Now there's two things that happen. If it's greater than the perfect length, it could swing where it has a side here, or it has a side, oh, I'm stuck again. There we go, side here. All right, so it could have here, swing it over here. It could make two different triangles. But if it's long enough where it's this long, when I swing this way, it can't hit a line. But swinging this way, if this side is long enough, it can hit this, right? If it's this long, when it swings, it won't hit this other side. So how do we decide what that's all about? So we have this side, and I'm just going to put it there for now. Let me do this. Move that over just a little bit. It was just bothering me. All right, so now, if it's this length could swing here or here, right? Oh, I'm streaking here. There we go. All right, so it could go here or here. So it could make a triangle in here. It's really hard to trace on this. So it could make this triangle, or it could make, let me get a different color, blue. It could make this triangle that still has this side, now goes out to here and goes across to here. All right, so we have two different triangles possible. And this happens when A is longer than the perfect length. So we're going to write that down as get some room. When A is greater than that perfect length, B sine A, then we could have two triangles. But we said we also could only maybe have one if it's too long. How do we decide if it's too long? Well, let's look at that. If this side is so long that it hits over here and doesn't hit over there, how would that happen? Well, it would have to be longer than B. If this side, A, is longer than the perfect length, but less than B, it'll hit both in two places. All right? So if it's less than the perfect, or greater than the perfect length, but A is also less than B, we get two triangles. All right? And we will get into how to solve that in a moment. So we get this. Now, there's also that situation we just said that if A is greater than the perfect length, but A is greater than or equal to B, well, then we only get one triangle, and it's that big triangle going out far to the right. All right, so these are our two different situations. If it's one triangle, we would just use law of sines because we have a pair, we just use it straightforward. If it's two triangles, I'm going to give you an example of that in a moment. All right, so that's our basic setup for this. That is when we do deal with this. Now, there is one thing that all of this counts on. All right, all this thing up to this point has been counting on one situation, and I want to make sure you're aware of this. When I drew this, I drew my initial angle as less than 30 or than 90 degrees. Whoops, less than 90 degrees. So everything I just told you is when our angle, I'll write given angle. Given angle is, oh, I just messed it up. All right, let me erase that. All right. When the given angle is less than 90 degrees. All right, this is what we get. Now, what if it's greater than 90 degrees? Well, let's go to a new page. All right, so the given angle is greater than 90. Then our picture changes. Because now when we do this, our picture is going to be similar idea to what we had before. We're going to have this, and this is going to go out forever, right? We don't know how far out it's going to go out that way. And then we're going to have an angle here that's greater than 90 degrees. So it's going to go back this way. And then we're going to have that piece that's floating out in space. We don't know where it goes, right? It's just out here. So in this drawing, again, that's going that way. This is our given angle. So this is our A. This is our side opposite, the one that matches whatever angle we have. And this is our side adjacent. So in this case, I think it's easier to see that if I go out here with another side, let me do this first. If I go out here with another side, there's only two things that can happen. I could hit out here and hit and hit and hit. There's no way if I get out to this far and I swing that I'm going to be coming back to hit another side, hit that side again. So it's either going to touch out here or it's not going to be able to make it out here. It's going to lay against this, right? It's going to swing down here. So how would I differentiate between those? Well, if this side is B length or less, we're not going to have any triangle at all, are we? It's just going to swing out here. If this side is greater than B, then it could start there and just start moving along there. These are lengths greater than B. So we could have something like that. So in this case, we don't need the perfect length when it's greater than 90 degrees. We don't need to worry about that. All we have to do is compare some basic ideas. If A is less than or equal to B, then we have no triangle. If A is greater than B, then we have one triangle. We just use law of sines to solve it, right? Because we'll have a pair and we'll just go from there. That's it, all right? So now we get to do some fun things. Let's do some problems. Let's do some exercises in this, some examples. All right. Let's do this. Let's do this one. I don't want that one. Okay. If I give you that, and we're just going to solve the triangle. All right, this is our example. And I give you that you have angle A is 72.2 degrees. Length B, or no, I'm sorry, that's supposed to be length C. Length C is 22, and length A is 21. And they want you to solve the triangle. So what we have to do is look at this and say, all right, what do I have? I've got an angle and two sides, and since there's a pair here, that's a non-included angle. All right, that's the process I want you to go through. So this could have, at this point, I know this could have either no triangles, one triangle, or two triangles. That goes back to a couple pages ago. All right, it's less than 90 degrees. The angle given is less than 90 degrees. I definitely have a non-included angle because I have a pair with the two sides. And so it could have 0, 1, or 2 triangles. So let's figure that out. I need to find the side adjacent, which in this case is C. I need to find my perfect length. My perfect length is going to be 22 sine 72.2 degrees. All right. And that length is 20.946. That in your calculator. So the length of that perfect length is that. So what that means is if I draw a quick sketch of my situation where I've got my angle going out that way, this is my angle A down here. This is my 72.2 degrees. This is my side that's 22. This is my side that's 21. What I just found out was that this side right here is going to be, or if it was the perfect length, this is the right angle side, it would be 20.946. So I have to look at my side A, the opposite side from my angle. This side is 21. 21 is greater than 20.946, right? It's close. I mean, this is really close, but this is longer. It's going to stick down a little bit farther. So this is going to come down this way and go just a little past, right? So that's 21. So what does that tell me? 21 is greater than this, but not greater than this, right? It's not so long that when it slides over here, it's going to go past this and only be able to make one. So this is one of those situations where my side 21 is greater than the 20.946 and 21 is less than 22. So this tells me two triangles. All right. And once I know it's two triangles, what I'm going to do is set up for two triangles. I am going to set up a kind of a chart that'll allow me to solve both simultaneously. I have two possible triangles, and I'm going to draw what they would look like in a minute. But I'm going to set up here and say I could have triangle 1 or triangle number 2. Now, triangle number 1 is I'm going to find its first piece just by doing everything. I know I've got the angle and the side opposite. So I've got 21 over sine of 72.2 degrees. And I have another side, and I'm trying to find the angle that's opposite that. So 22, and we'll call that, since that was side C, right? C equals this. I'm going to call that sine C. And with this, I can find angle C in my first possible triangle. All right, so if I do that, I'm going to draw this a little longer. If I do that, I can go here and say, all right, so I know that sine of C is equal to 22 sine 72.2 degrees divided by 21. And somewhere in here, I just got really fat writing again. So I'm going to go back and make this smaller so you can read it better. All right, so we got this now. And when I do that, I find that the sine of C is equal to 0.9974. Again, when you use your calculator for this, make sure you're in the right mode. All right, so sine of C is equal to that. So now in order to find C, if I take sine of each side, that key on your calculator that says sine inverse, it's the arcsine function. That means the angle whose sine is. So here, C would be the answer, and that's equal to sine inverse of this. So when we do that, we get 85.922 degrees, or we can say angle C is 85.9 degrees to the nearest tenth. So we have this. All right. And what has that done for us? Well, let's go back to our triangle and try to see what it looks like. 85 degrees is an acute angle. So what this is going to be is, let me get this back and that, and let's do it in blue. All right. So what this is going to be is an angle that is 85 point something. We know it's going to hit right about here, right? Less than 90 degrees. And it's going to give us this triangle that is right here, right? So we have that triangle. Well, what we know, though, is that if I go and do the swing of that angle, let me do this. If I have the same thing here and I swing it over here, it could also be over here now, right? If I swing that over, this one would just swing over here, and I would have that triangle that would be going across here and across here, right? So this one would have this angle. So what I'm looking at now is I need to solve for this angle. What I'm doing is I'm doing both of these simultaneously, both of these two triangles, because it's the quickest way. Once you see one of these, you'll see I wouldn't do all this talking and we would just go right into it. But I'll do another one after because I want to explain this. So we just found this angle. Now this side and this side are the same. So isn't this right here an isosceles triangle? If this is an isosceles triangle, the base angles are equivalent. This angle and this angle are equal. So I just found this angle. This angle is equal to this angle, and now I need this one. Well, these two add up to 180, don't they? So that angle I found down here, this angle that's 85.9 degrees, whoops, did not want to do that, is this is that angle up here, right here. So I know when I'm looking for this angle, what I'm going to do is I'm going to just go over here and say 180 degrees. And this is another angle C. I'm going to write it that way. I'm sorry. I'll get rid of this stuff. All right. I am going to write this as angle C for triangle 2. So I can solve for angle C in triangle 2 right away by saying 180 degrees minus that angle I just found, 85.9 degrees. So this is going to be 94.1 degrees. And I have angle C for my second triangle. So see what I'm doing, and now again, just to recap, all I did was, knowing I have two triangles, I set up for two triangles, then I used law of sines, right? I started out first step, law of sines. I found the angle that matches the other side I have that's not part of the pair. And then I went to my second triangle and said, all right, well, the other triangle, this one here, has to be the supplement to that original angle. So I'm going to take 180 minus that, and I get the other triangle, or the other angle. So now I've got two pairs. I've got two sets of what I need. And I got two angles, more importantly, because I know angle A was 72.2 and angle C is 85.9. Now I can go about solving the rest of this triangle, because guess what? Now I got two angles. If I've got those two angles, I can find angle B now, because angle B is going to be 180 degrees, because all the angles add up to 180, minus the two I already know, 72.2 degrees plus 85.9 degrees. And so I know this is going to be 180 degrees minus 158.1, I think. Let's see. 72.2 plus 85.9 is 158.1. And that means that our angle B for the first triangle is 21.9 degrees. Now I can go ahead and do that on the other side too. I can do that over here because I have my angle A and my angle C for the second triangle too. So I can say angle B is equal to 180 degrees minus, and I have the 72.2 degrees again, plus, 94.1 degrees. And that would be 180 degrees minus, well, 72.2 plus 94.1 is, what do we get, 166.3 degrees. And that means we get 13.7 degrees for angle B over here. And so for both triangles, now we've solved for all of the angles. Now we can go back and use the original ratio we had here, right? Always go back to your givens if you can. We need side B still. So what we're going to do is use that original ratio of 21 over sine 72.2. And we're going to say that's equal to the length B we don't know. And we're going to use sine of that one we just found, 21.9. Of course, you got to be careful that you found right ones as you went along here. And then we can say B equals 21 sine 21.9 degrees over sine of 72.2 degrees. And that means B equals, let's see. Again, double checking that your calculator's in degree mode. And we should get 8.226. So we'll call it 8.2. So a length of 8.2 for B. And that's all of the first triangle. Triangle, we found the three missing pieces, both the angles and the side that's missing. We have both angles here. We got to find the side that's missing. So here we do the same thing. I do 21 over sine 72.2 degrees. And that's equal to length B over sine of B, which is 13.7 degrees. So B here will equal 21 sine 13.7 degrees over sine of 72.2 degrees. So that makes B equal to 21 sine 13.7 divided by sine of 72.2. And we get 5.2. And we've got our second triangle solved. So these are our two sets of solutions. These are two possible triangles that would come from this initial set of information. All right. So that's what we got. Now, that sounds pretty involved, and it sounds like it's incredibly difficult, but it really isn't that bad once you get used to it. If you go through this and you think of what you use in this situation, all right, so let's say we're given, I want to write this down as kind of a process. Given two sides and a non-included angle. And there is one other way of doing this, guys, but we'll show you that in class. Some people will like it, some won't. I want you to try this first. All right, non-included angle. If you're given two sides, the first thing you got to ask yourself is the angle less than 90 degrees? Right there for a second. Or is the angle greater than 90 degrees? Angle greater than 90 degrees. All right. So again, if it's equal to 90 degrees, we use right triangle trig, right? I hope you know that. So if it's 90 degrees, it's a right triangle. You just use right triangle trig, use your ratios, and you're good to go. So less than 90 degrees, what do we have to do? Well, if it's less than 90 degrees, we need to find the perfect length first, right? And then we need to see how A compares to it. If A is equal to the perfect length, well, then we have a right triangle. And there's one solution. If A is less than the perfect length, right? Perfect length, again, remember, is I'm going to call it now the side opposite. It's the one that doesn't match the angle times the sine of whatever angle you were given. All right. That's the perfect length. So if A is less than the perfect length, that implies that we have no triangles. So therefore, no solution. All right. Again, I'm going to try to keep these separate. So the other option, if A is greater than the perfect length, well, there's two things that could happen here. One thing is if A is greater than the perfect length, but A is less than B. When I say B, I mean the side opposite, right? Our A is the side opposite, B is the side adjacent. So if A is less than the side adjacent, we, in this case, would get two triangles. If A is greater than or equal to B, then we get one triangle. So there's only this one case where you have to find two triangles. The rest, you're just going to be using law of sines like we did in the very first problem, and we used for both angles or triangles in the second problem. So that's what we have. That's that situation. And then you solve accordingly. Now, if it's greater than 90 degrees, you only have to do one thing. All right, you have two situations. You compare A, that side opposite. If A is less than the side adjacent or equal to side adjacent, that we call it B, right? If it's A is less than or equal to that, that is going to imply that we have no triangles. If A is greater than the side adjacent, then we would have one triangle. And we just use law of sines to solve that, right? And again, anytime you get to any of these, you're going to start with the law of sines. That's what you did with all of them after you figured out what you were dealing with. So that's pretty much the summary, guys. And I know it sounds confusing at first, but if you follow along with this and follow this procedure, you'll see that it works out pretty well. Let's see. Let's do one more example. And again, I know this is going to be a long video. So if you feel confident, go ahead and do your work now. I just want to give you an example of a greater than 90 degrees. Let's see if we have one more example. If I gave you angle A is 42 degrees. I'm actually going to do this here. And length A is 22. Length B is 12. This is not going to be the type of example I told you, but it's the one I want to do. If we have this, we have, again, this is angle A, sorry. Angle A, length A, side B. In this situation, we have a pair, so this is definitely a non-included angle, right? We have two sides in an angle and one of them matches, so we have a non-included angle. First thing we want to do is find that perfect length, right? So in this case, we're going to do 12. The perfect length is going to be 12 sine 42 degrees. And 12 sine 42 degrees is going to be 8.029. So that is equal to 8.029. So that's our perfect length. So if we draw that situation we have, this side is 12, this is 22, this is 42 degrees. Our perfect length is 8.029. So this is much longer than it. It's so long, in fact, that it's longer than both the perfect length and the side adjacent. So we have one triangle here. So being that there's one triangle, we just go ahead and solve it. I have a pair, so I'm going to use 22 over sine of 42 degrees. And I'm going to solve for, well, I know B, sorry. I'm going to solve for angle B by saying 12 over sine of B. So sine of B will equal 12 sine 42 degrees over 22. And that means that angle B, when I take sine inverse of that, I'm going to do 12 sine of 42 in my calculator, divide it by 22. And then I'm going to do second sine or sine inverse of that answer. and I get 21.4063 degrees, so 21.4 degrees. So now I've got that. With that, I can find angle C right away because I already know angle A and B. So angle C is just going to be 180 degrees minus 42 degrees plus 21.4 degrees. So that's 63.4. So this is going to be 116.6, I believe. 180 minus 42 plus 21.4. Yeah, 116.6 degrees. So now I've got that third angle. Now I just need to find that last side. And I'm going to go back to what I was given, 22 over sine of 42 degrees, and set that equal to C, the length C I'm looking for, over sine of 116.6 degrees. And that means C is equal to 22 sine 116.6 degrees over sine of 42 degrees. So 22 sine 116.6 divided by sine of 42 is length C would be 29.398, so we'll call that 29.4. And we got our triangle solved. So again, just an example of what you could have there. And you've got more to work on in your book. So go at it and do your best with this. I know it can be confusing at first, but stick with it, work at it, and we'll go over your questions tomorrow. Have a wonderful day.